Hello, this is Miraj Patel here, and today we are going to continue our topic of dynamics, but now we are going to talk a little bit more about centripetal acceleration and a little bit more complicated dynamics problems. And so we already talked about free body diagrams in the last video, but I forgot to show you this one method or one strategy of solving a problem where we sort of rotate the axis. And so this is a very useful method when solving free body diagram problems. And so here we're going to do a problem where we should rotate the axes and show you how that works. So so here's our problem. A box is on a 30-degree inclined plane and weighs 10 kilograms. The coefficient of friction of the ramp is 0.4. What is the acceleration of the box? So first, I would think of the situation. So draw a picture, and then from the picture, then I'll draw a free body diagram. So if you imagine an inclined plane and a box that it should be 5 kgs instead, sorry, in this problem. But so just imagine a box on a plane, and then now draw a free body diagram. We have pretty much three forces: the normal force, which is perpendicular to the surface; weight, which is always straight down, which is mg; and then friction, because I gave you a coefficient of friction, so it's off to the side like this. And this arrow I told you I'm using to represent the acceleration. So this box is going to slide down. And always remember, if you're going to write an acceleration arrow, draw it outside the free body diagram to the side, like this. And so basically there's three forces: weight, normal force, and friction. But before we get started, let's think about this situation. There are two forces right now that aren't aligned with the normal x and y axes. So right now it would be hard to solve the problem. But we can rotate the axes so only the weight is unaligned, and so the acceleration is on the x-axis. And so when you're solving these problems, and especially on an inclined plane like this, you would want the acceleration to be on one of the axes. And since the normal force and friction are perpendicular to each other, we can twist the axes so everything is aligned with that axis with except weight. So that will make it much easier to solve the problem. So let's talk about rotating the axes. So imagine a normal coordinate grid, and now twist it counterclockwise 30 degrees so the x and y axes match up with the friction and the normal force. So the dotted lines represent the original axis, and then we twisted it 30 degrees upwards on every side. So that now the inclined plane is like, imagine it right here where the 30 degrees is. And so now the friction's on the x-axis, and imagine the normal force, and it's parallel with the y-axis. And then the acceleration's down the ramp, so it's with the x-axis. So by twisting it, we only have to break one force into components, which is gravity. Because gravity is straight down, like this blue arrow here, and it does not match up with any of these axes, but we can break it down into components so they do match up. So here's our free body diagram of the situation, and I drew the two components of gravity and broke them down for us here. So since gravity is 30 degrees from the y-axis, because this is a new y-axis, and since we tilted everything 30 degrees counterclockwise, gravity is 30 degrees from the y-axis. So Normally, if you measure something from the x-axis, cosine will always be in the x direction, sine will always be in the y direction. But since we measured this from the y-axis, cosine is in the y direction and sine is in the x. But, so this is a new thing. If you measure something from the y-axis, cosine will always be in the vertical direction, or y, and then sine will be in the x direction. So 30 mg cosine 30 the is with the normal force, and then mg sine 30 is with the friction in this case. So it's important you know that when doing sine and cosine. So the normal force and mg cosine 30 must be equal to each other, because we know the box isn't sliding up and down. It's going side to side. So these two, by definition, must be equal because there's no acceleration up and down. It's all to the side. So we need to write an equation for the acceleration in the x direction. So we do the net force equals mass times acceleration, or the summation of forces. And since friction is to the right, and the component of gravity is to the left, I'm going to call the component of gravity negative and friction positive. So friction minus the component of gravity equals mass times acceleration. So since the normal force is the same as mg cosine 30, and we know the coefficient of friction, we have to multiply the coefficient of friction right here, 0.3, by the mg cosine 30, because that's equivalent to the normal force. So that's how we get friction, minus mg sine 30, which was the same as before, equals mass times acceleration. So if we plug in all our numbers, 0.3 times 50 is the mg, and then cosine of 30 is 0.866, minus mg, which is 50, and then sine of 30 is 1/2, equals 5a. And so if we do this and we divide each side by 5, the acceleration will be negative 2.4 meters per second squared. And the sign works out perfectly because we called the left to the left negative, and this box is definitely sliding to the left. It's going down the incline. So this problem definitely makes sense and checks out to be correct. Okay, now we're going to go into centripetal acceleration, and I'm sure most of you have heard of the word centripetal, and centripetal basically means like relating to a circle. So basically, centripetal acceleration is the phenomenon when you take a turn at a constant speed, the velocity changes, and therefore there's an acceleration, because velocity is magnitude and direction, if you remember from kinematics. And so if we change direction, by definition we're changing the velocity, so we're accelerating. And you can feel this whenever you drive in your car and you take a turn and you don't really slow down. You can definitely feel that acceleration as you go around the turn. It almost feels like it's pulling you away from the turn. But so that is what centripetal acceleration is. And so let's explain briefly what centripetal acceleration is and how it works. And so for instance, let's take for example a fly is on a record player, and the record player is spinning with a constant velocity. So here I drew a little weird picture. So the circle is the record player, and then these two swirly things are the flies, as before and then after. So the record player is spinning around, so it starts here and then moves there. So the velocity of the fly is tangential. So that just means that when anything's spinning, the velocity is always tangent to where the fly is. So if the fly is here, if we stop the record player, the fly would want to go straight forward. If the fly was here at the top, if we stop the record player, it would want to keep going straight forward. So basically, velocity is always tangential to a circular path. So if something's moving in a circle, wherever the location you look at it, the velocity is tangential. So since acceleration is a change in velocity, we must do final velocity minus initial. So we have to subtract these two vectors. So when you subtract vectors, you basically place one of the vectors down, and then you put the other vector on the tail of the first vector. So this is how it looks. So I place the first vector, and then I put the next vector on the tail of the other one, so they share. And so this is a resultant vector, and this is the change in velocity or acceleration or centripetal acceleration. And the resultant vector of a velocity when moving in a circle at a constant speed will always point to the center. So that is the cool thing about centripetal acceleration, that it always points to the center. And that's because there's a force always pointing to the center, keeping it in a circle. And so this will always hold true. So if you're going in a circle at a constant speed, whichever 2 points you look at, they will always point to the center. So that's great. So centripetal acceleration is basically an acceleration caused by a turn, and it's because you change the velocity when you change direction. And centripetal acceleration, the formula is v squared over r, or r omega squared. And omega basically is just rotational velocity in radians per second. So it's basically saying how fast you're spinning omega. And radians is just a relationship between the radius and circumference. And circles, each circle is 2 pi radians, or about 6.28 radians. And so it's 6.28 times the radius is one complete revolution in a circle. So in our AP1 physics class, we only deal with problems with constant velocity and radius, because if you change one of those, then the problems become much harder, and it will require higher level math. And if we want force, like using Newton's second law, we still use force equals mass times acceleration, but instead of normal acceleration, we just put centripetal acceleration as the acceleration in the formula, and we just need the mass, and then we got the force that's holding it inside the circle. So here, let's do a simple basic problem for centripetal acceleration. So what is the centripetal acceleration of a ball on a string that is moving 2 meters per second on a half-meter string? So if you look at the formula, we have velocity and radius. So we should use the first form of centripetal acceleration. So 2 squared is 4 over the radius, which was 1/2. So 4 divided by 1/2 is 8. So this string, or this ball, is accelerating 8 meters per second squared. So this is how you use the formula. You just need the velocity and the radius, or the radius and the angular velocity. So here, let's do an artificial gravity problem. And so we're gonna use a gravitron in our problem. So there's a gravitron that's designed to make you feel 5 times as heavy as you are on Earth. The radius of the gravitron is 6 meters. How fast does it have to spin to achieve its design? So a gravitron is basically a large ring in which you are against the wall, and it spins so fast that you're pinned against the wall, like these people. And some of them, they actually move the whole floor down to show that you're pinned against the wall. And basically it's just using centripetal acceleration to keep you pressed against the wall. So So we want the centripetal acceleration to be 5 times what it's on Earth. And Earth is 10 meters per second squared, so 5 times 10 is 50 meters per second squared. So this is the acceleration we want. So we use this formula, and instead of solving for A sub c, we want to solve for velocity. So we just multiply each side by r, the radius, and take the square root of each side. And so after doing that, we just plug in the information. So the centripetal acceleration we want to be 50, and it's 6 meters in the radius. And so if we do this, we will get 17 meters per second. So the gravitron has to spin at 17 meters per second to make it feel like you're 5 times as heavy as you are on Earth while it's spinning. So let's talk a little bit about banked turns. And so banked turns are turns in which there's an incline, so you don't have to reduce speed to turn. And so here's an example of a banked turn with this bus is going on. And so they help reduce, help make, allow you to go faster on sharp turns or small spaces. And you can often see these in race cars or racetracks, and for very fast turns, like on the highway. If you going like 70 miles per hour, instead of slowing down everyone to 50 miles per hour to make a turn, they might just incline the turn slightly so that you can keep on moving fast. And so the reason why you can go fast, or you can go faster on bank turns than normal non-incline turns, is because the normal force helps contribute to the force that's keeping you turning in a circle. Because on normal flat turns, only friction is keeping you in the circular path. But on banked turns, the normal force, or a component of the normal force, is helping you stay within the circle. And the steeper the incline, the more of the normal force is keeping you in the circle. And so the greater you're gonna stay, the better, the faster you can move whilst making a short turn. So here we're gonna do one bank turn problem. And so here's the problem. A car is turning around a 50-degree banked turn that has a radius of 20 meters. How fast can it travel around the curve? Assume there is no friction. So here is a picture, a simple picture of the turn. So here we have an incline, and these are the two wheels and the seating area, and it's 50 degrees. And so we want to know how fast the car should go so it's a safe speed. So let's draw a free body diagram. So let's include the forces. We know that there's three or two forces because we're assuming there's no friction. Friction really makes this problem significantly more involved. So I just decided just to assume it's an ideal curve. So basically there's just a normal force because the ground is definitely supporting the car. And we have weight, like always. So weight is straight down. Normal force is perpendicular to the surface, so it's straight out, like this to the side. And so if we include the forces, there's we have to break down the normal force into components, so it's on the x and y axis. So Fn cosine of 50 is in the vertical direction because imagine that this angle here between this black arrow and the top red arrow is 50 degrees. So sine is opposite over hypotenuse. So this is Fn sine of 50, and this is Fn cosine of 50 because this is the adjacent side. So remember, when you're measuring from the y-axis your angle, cosine is vertical, sine is horizontal. It's the flip side of when you measure from the x-axis. So, in the y direction, uh, we know that the car isn't accelerating upward or downward. It's staying the same in the y direction. So if the sum of the forces is 0, these two forces are exact opposite, so they must be exactly the same. So weight must equal Fn cosine of 50. So now we have the second part, which is in the x direction, and we know the car is accelerating in the x direction because it's turning in the x direction. So net force equals mass times acceleration, net force in the x. So we have to add the forces, and so since there's only one force in the x direction, which is Fn sine 50, sorry, I forgot to type it here. So Fn sine of 50 equals mass times acceleration, and so we use the first little part here to to solve for Fn. So to isolate Fn, we just divided each side by cosine of 50, and we got this expression here. Fn equals mg divided by cosine of 50. Now if we substitute this into the second equation here, we will combine both equations together. And so we will get mg sine of 50 over cosine of 50 equals mv squared over r. And I'll remind you that tangent is equal to sine over cosine. It's one of your identities, and you'll learn this in trig class. And so we can just simplify this sine over cosine to tangent. And since there's two m's on both sides, we can go ahead and cancel those out, like so. And so all we're left is Rg tangent of 50 equals v squared. So if we undo a square, we do a square root. So we square root both sides and we get square root of Rg tangent of 50 equals the safe velocity, or the speed the car should travel. So 20 is the radius, 20 meters. 10 is the gravity. And then tangent of 50 is just a constant, so we just take the square root, and it says the car should travel at 15 meters per second. So that's at a safe speed. So thank you for watching my physics video. Today we talked about free body diagrams with centripetal acceleration and a little more complicated complicated free body diagram where we had to rotate the axes so you could better do the problem. Next, the next video is going to be about centripetal acceleration in planetary motion. So we're going to talk about Newton's law of gravity, and we're going to sort of combine it with what we're talking about now with centripetal acceleration. So if you please, if you enjoy this video, please like the video and spread the word to your fellow classmates and other people you know that are taking physics. So email me any questions at mpatelbuccaneer@gmail.com, and please practice these problems and you will understand the ins and outs. You just have to go find any sort of practice website. Like, you can go to the OpenStax college physics textbook that I've been suggesting, and just practice several problems, and have someone else look at your work, and keep on repeating the problem until you can do it without even looking at your notes or anything like that. And for chemistry tutorials, if you're taking chemistry, please visit my website, buccaneerchemistry.weebly.com. Thank you for watching, and I hope to see you next time.